Everyone, in this video I'm going to talk about some applications of the Riemann-Lebesgue theorem, specifically with a few famous examples of the Dirichlet and Thome functions. So just to recall, the Riemann-Lebesgue theorem says that if I take a function on a closed interval that is bounded, and I consider its discontinuities d sub f, then f is Riemann integrable if and only if the measure of that set of discontinuities is 0. So for our first example, I'll go over the Dirichlet function. This is probably the most famous. It's hard not to find this in an introductory analysis textbook on Riemann integration. So it's called the Dirichlet function, and it's kind of a wacky function where you set the function equal to 0 whenever x is irrational, and you set it to 1 whenever x is rational, and we're working on the closed interval 0 to 1 here. So the function looks a little bit like this. So whenever I'm rational, I output to 1, but since the rationals are dense, this really looks like a super thick, dense cloud, and when I'm irrational, I set it as 0. So again, I have these dots here. Since the irrationals have measure 1 here, I've drawn this more like a solid line. And you can pause the video here and think about, so ultimately what we want to do is apply the Riemann-Lebesgue theorem. So we want to look at the discontinuities here rather than trying to build a partition. So you can pause the video and think about where you think the function's continuous and where you think it is discontinuous. And when you come back, I will try to claim that it is discontinuous everywhere. So this isn't too bad to prove, actually. So let's let x be in 0, 1. I'm going to set epsilon to be 1/2. And I'm going to set delta positive. If x is rational, then since the irrationals are dense, in 0, 1, then we can pick an irrational such that y is in b delta of x. And so the difference here is 1, which is strictly greater than 1/2, which is the epsilon we chose. So we've shown that f is discontinuous on the rationals. I'll switch colors here. So if x is irrational, then recall that the rationals are also dense. So we can pick a y that's in our ball around x such that y is rational. So f of x minus f of y is 1, which is greater than 1/2, which is equal to epsilon. Therefore, df is the entire space that we're considering. And so the measure of df is just 1 minus 0, or 1, which is strictly greater than 0, and that tells us that f is not Riemann integrable. So if we go back up on this picture, though, it's kind of ridiculous to say that we can't integrate this function. Or not ridiculous, I guess, but it's not Riemann integrable. So if that was our whole world, we'd just say, okay, we give up to try to integrate this. But this function is actually Lebesgue integrable. And intuitively, the reason why you should be able to integrate this is because it's sort of motivated why I drew the irrationals as a solid line and these as dotted lines here. Now, of course, if you zoom in, really, this looks like a straight line also from sort of any zoom level. But the point is that rationals have a set of measure 0, or are a set of measure 0 because they're countable. The irrationals basically are pretty much this function is equal to 0 pretty much everywhere in the domain, other than a very small set here. So this integral should be 0 intuitively. And it turns out that if you define an alternate way of integration, the Lebesgue integral, then this function is actually integrable. So then I'll show you guys another example over here, the Thome function. This one will actually end up being Riemann integrable. So I claim that its set of discontinuities, it is continuous on the set of irrationals, but it is discontinuous on the set of rationals. So it's a similar setup. I set my function as 0 on the irrationals, and I do a funny little rule on the rationals. So whenever x is rational, I find its irreducible form. So p and q are coprime here. They have no common members of their prime factorization, so, or irreducible form, whichever way you prefer to formulate it. And I take 1 over its denominator. So, for example, f of 1/4 is 1/4, but f of 2/4 is 1/2, f of 3/4 is 1/4. And so this function kind of looks like, because 2/4, right, 2/4 is 1/2. I need to get it into irreducible form. And similarly, f of 1/8 is 1/8, sorry. F of 2/8 is 1/4. F of 3/8 is 1/8. F of 4/8 is 1/2, and so on. So the idea here is that if I take my function, so this is, it's going to max out its, let's call this 1. It's only going to be equal to 1 over here. So this is 1/2. So here at 1/2, I'm going to get this. And at 1/4, I'm going to get this value. And then if I cut this into an 1/8, 3/8, 5/8, 7/8, and 1. 1 is going to be 1. The point is that each time that I subdivide here, I'll go one more level. I'm just cutting in half because it's a bit easier to 3/16, 5/16, 7/16. 13/16 and 15/16. The point is that these get smaller and smaller because it's 1 over the denominator, right? I don't care about the numerator in the definition of this function. Okay, so then this process would continue going And then, you also have like prime numbers, right? So I've been cutting in powers of 2 here, but there's also like prime numbers and everything. And basically what's going to happen is, similar to last time, these points sort of look isolated, and you actually get sort of a dense looking line here on the irrationals. And so it's also relatively easy to see here why you get discontinuity of the rationals, right? So if I look here, there's space between, there's little jumps here according to the weight. So if I zoom in super far, I'm also going to see a point here that's going to look like a big difference similar to this here if I keep zooming in. So we're going to be discontinuous on the rationals, but continuous on the irrationals. So continuous on the irrationals is actually easier to show. So I'm going to say let x be irrational. We're going to start with this one. And I'm going to say let epsilon be positive. No, actually, this is the harder version. Proving discontinuity on the rationals is easy. So again, we're on 0, 1. So again, this is just by density, and I'm going to say let x be p over q in irreducible form. And I'm going to set epsilon to be 1 over q plus 1. You could set it as 1 over q, but I like to be q plus 1 just to be safe. So we have the irreducible form, and I'm going to take that as epsilon. And then let delta be anything positive. Pick an irrational in B delta of x. Same density argument. So f of x minus f of y is 1 over q, which is greater than 1 over q plus 1, which is epsilon. So this says the rationals are contained in a set of discontinuities. And then I'm going to show that irrationals are not, so that we get exact equality of set of discontinuities now. So let x be irrational now, and epsilon be positive. Okay. Let q be such that 1 over q is less than epsilon. Okay. Now, I'm going to let A be the set of all x and q. Well, we can just even do this. P over q in 0, 1 such that, or P over, let's do R over S. R over S in 0, 1 such that R and S are in the naturals, and S is less than or equal to q. And I'm going to take delta to be the minimum of my point x. I'm going to take half that distance. Okay, so why can I write minimum rather than infimum? That is because A is finite. right? I've given you a specific Q, and yeah, so sorry, this is in irreducible form. So A is finite, so I can take its minimum. This is a very crude approximation. You can do it more detailed than this, but it's finite, so I can take a minimum. So we have that delta is half that distance. So I'm going to claim, so let's take any y and b delta of x, intersect q. Or yeah, let's just, okay. If y is irrational, we're done since f of x equals f of y. So let's suppose y is rational. Okay. We know that x minus y is less than delta over 2. That tells us that y can't be in A. Because the distance is half that of the minimum. So by definition of A, y equals p over, so q has been set. Let's just use r over s again, where s is strictly greater than q. So the absolute value of f of x minus f of y, well, f of x is 0, so this is just f of y, is 1 over s, which is strictly less than 1 over q, because s is strictly greater than q, and that is less than epsilon. Which tells me that every place, every irrational is continuous. So the set of discontinuities is exactly equal to the rationals, which implies that the measure of the set of discontinuities is 0, and that this function is in fact Riemann integrable. So there's just a few examples. And hopefully this motivates Lebesgue integration a bit. And so the next video, I'll get into Lebesgue integration. Thank you guys for watching.